And how about the screen? Is it visible?
Yes, sir.
Okay. Today in this session, we will be discussing about magnetic material. It is a continuation of the previous topic where we had stopped during your offline session. Magnetic materials. If possible, try to make a note of whatever we discuss in the class and prepare a small note of every session with respect to the equations, with respect to the concepts or content, what has been dealt in the online sessions. So just a quick review of what happened in the previous class. So we are aware about the susceptibility concept. Susceptibility is denoted as psi. So what is susceptibility? Susceptibility is possibility of getting something. So here we are talking in terms of magnetic materials. So if you say, if you expose a material, if you expose any material to a magnetic field, suppose this material is exposed to a magnetic field. Okay, so field is here somewhere. And the possibility of getting this material susceptible to the magnetic field. So the process of being or process of making or converting this material to a magnet. Okay, you call it as a process of magnetizing any material due to magnetic field, called as magnetization. So thereby exposing one material to magnetic field. So what is the susceptibility? How good a material is susceptible of getting magnetized? So this we have studied in the last class. So usually what happens, susceptibility of material decides magnetization over given magnetic field. So susceptibility is defined as psi is equal to, this is magnetization M over magnetic field H. So it is ratio of magnetization over total magnetic field. So what is magnetization then? So magnetization M is equal to psi, that is susceptibility, into magnetic field. So this is one important relationship between magnetic field, magnetization and susceptibility. This is not X, this is psi. So if you make a note, the ratio of magnetization to total magnetic field is called as susceptibility. Okay, now I'll just, am I audible?
Yes, sir.
Okay, fine. You please interrupt me or just let me know if there is any disturbance in the screen, on the screen, or maybe inconsistency in the network or any other issues. Just let me know on WhatsApp. Just message me or text me. So any material is made up of atoms in which electrons revolves in an orbital motion. So here, if you consider this as a nucleus, so any material is made up of atoms and electrons here. So electrons are revolving around in orbital motion. And this phenomenon is called as orbital motion of an electron with respect to the nucleus. And also the electron rotates on its own axis. So electron rotates on its own axis, and this motion is called, what is this motion? This is called spinning motion. Electron spins, and this is orbital motion. Due to these orbital and spinning motion of electrons, there will be an internal magnetic field which will be produced. Okay. So due to these two concepts, orbital motion of an electron and spinning motion of an electron leads to what? Leads to internal magnetic field. You call it as atomic currents. Internal magnetic fields. Okay. And say we have a conductor and we have a bound current, say IB. Suppose if this is a current carrying conductor. Okay. So this current is called as IB. If the bound current IB flows through a closed path, also you can assume another closed path conductor like this as well. So here you have a bound current called IB, which encloses a differential area of ds. So this is enclosed. So this encloses a differential area of ds. So this area is called as ds, and the bound current is IB. The magnetic moment is given by small m. Small m is magnetic moment, and it is given by m is equal to bound current into differential surface area. Okay, this can also be written as IB differential surface some value, and usually the surface will be normal to what? The current IB. The orientation is normal to the magnetic field. Now, this is referred to as magnetic strength. IB into ds gives us the magnitude, or you can call it as magnetic strength. And this AN gives direction or orientation. It's a unit vector. So it's the magnetic strength, IBds or IBdN or IBdV if it is a volume surface or if it's a line conductor. Okay, so this is called as magnetic moments. What is magnetization? So magnetization in any material is associated with an atomic current loops generated by orbital and spinning motion of electrons. If there are n number of magnetic dipoles, suppose if you have a small volume delta V, this would be the atomic currents. This is the atomic currents, say, and randomly oriented. Orientations are random without magnetic field, where B is equal to 0. Therefore, M is also equal to 0. Magnetization is 0 here. And these are called as magnetic dipoles. These are called as magnetic dipoles. Suppose if you try to make this small volume being excited or bring it into the content of magnetic field, then you could see the same volume and of course the atomic currents and orientations of dipoles will get aligned in the same direction. So this is when it is subjected to external magnetic field. So this is external magnetic field. When you have B is equal to some value and H is equal to some value. So on the same dipole moments are subjected to magnetic field. You could see the orientations and the magnitude as well as the directions with respect to magnetic field. Now, if there are n number of magnetic dipoles, see here you have 3, right? Here you have how many dipoles? You have m is equal to 3 dipoles. This is 1, this is 2, and this is 3. If there are n number of magnetic dipoles in a given material or in a given volume, so I have an equation. So I write it as mt, where this t represents, t is a variable which represents number of dipoles. Mt is equal to summation k equal to 1 to n delta v. This is number of dipoles. It is simple summation of all the dipoles with respect to this volume. Number of dipoles inside the volume. So this is total magnetic dipole moments. Total magnetic dipole moments. Kindly make a note of these equations. Total magnetic moments, dipole moments is given by mt is equal to k equal to 1 to n delta v mk. So now, how do you define magnetization? So magnetization is a concept where I will try to understand how many number of dipoles are there per unit volume. Okay, so I could say MT. This is total number of dipoles per unit volume, and okay, per unit volume, and the volume shrinking to 0. Delta V tends to 0. This is very important equation. It is just like the previous divergence and curl concepts what we have studied. With respect to the divergence concept, if you understand a divergence with respect to a volume, with respect to a very small volume, so you understood this divergence concept. That is del dot D is equal to rho v, Maxwell's first equation. So divergence of any given vector, so when the volume is shrinking to what? 0, you call it as divergence. Similarly, you have a magnetic field here. You have a magnetic field, and then now you say the surface shrinking to 0. Delta S been made to 0 in order to understand what? Curl of H. You understood curl concept at a point, divergence concept also at a point by making this volume shrinking to 0. Here also I am trying to shrink this volume. See here you have n number of moments. Here you had a dipole moment. Here you have another dipole. There are n number of dipoles, right? So these dipoles will have what? Both orbital motion as well as spinning motion. Okay, and this is an atomic current, and this is an internal magnetic field which is generated due to atomic current. So there will be an atomic current due to orbital and spinning motion, and this orbital and spinning motion will generate what? Internal magnetic field. I would call it as IM. So this magnetic field I refer to as magnetization when the volume shrink to 0, when you're trying to take the ratio of total magnetic moments or dipoles over delta V. In simple, magnetization is a concept with respect to the ratio of dipoles over volume, and volume shrinks to 0. Okay, so this can be elaborated as magnetization M is equal to, so I'll write limit delta V tends to 0, 1 over delta V. What is MT now? MT is equal to this summation 1 over delta V summation K equal to 1 N delta V mk. Ampere meters. So this is one more equation which you need to remember. So what is magnetization? Magnetization is equal to number of magnetic dipoles over delta V over a small volume, where small volume shrinks to zero. So magnetization is understood at the atomic level. Okay? Magnetization is understood at the atomic level in terms of orbital and spinning motion generating internal magnetic field. Is that okay?
Yes, sir.
Okay, so I'll go to the next content. So now here I'll write at the top of your screen. Suppose if you have a bound current, say you have a bound current like this, which encloses a small surface area ds, and this is what? IB, bound current IB. So this is IB. This is a conductor, guys. This is a line conductor. If you just try to unfold this conductor, this is a line conductor. So this happens to be a bound current with some length. So this produces what? This produces a magnetic field. Okay, this is a magnetic field. So you'll have a magnetic field here. So I can write an equation, try to extend the relationship between a bound current over a closed path. So what is the relationship between a bound current over a closed path? IB is equal to, now very recently we have derived the equation for M, that is magnetization. So I'll call this as a contour integral of M into dl. So it is just a summation or an integration of a magnetic field over the length will be equal to what? The total current. So here also you'll have magnetic field. So here also you have magnetic field. So everywhere you have a magnetic field within this closed surface. So these many magnetic fields, the sum of these magnetic fields will be equal to the total bound current. Okay. But we know that total current is equal to IT. Total current is equal to bound current plus free current. I call this free current as an electronic current, the current which is produced due to the movement of free electrons. See guys, I repeat, the total current will be the summation of bound current. This bound current is due to orbital plus spinning motion of an electrons and internal magnetic field. This is represented in terms of magnetic field and free electrons. This is current due to free electrons. So what is total current? Total current is equal to bound current plus free current. And now I can equate this total current IT using Ampere circular law. IT is equal to line integral of total magnetic field H into dl. This is based upon Ampere circular law. So I can equate these two equations. IT is equal to integral H dl. Make a note of these two equations. But what is total current is equal to? I can write it as B is equal to mu naught H in free space. Okay, I can write B is equal to mu naught H in free space. Therefore, H, that is magnetization, is equal to magnetic field. Sorry, magnetic field is equal to B over mu naught. If I substitute this equation into a total current, okay, if I substitute this equation here, I'll get IT. IT is equal to line integral or contour integral B by mu naught into TL. And I know IB is equal to, what is IB is equal to? MdL, that is magnetization into dl. So can I calculate the free electrons or free current here? So what is the equation for total current? Total current was is equal to IB plus IE, right? IB plus IE. So can I calculate free current knowing IB and IT? So what will be the equation for free current? Free current IE is equal to IT minus IB. So this is IT minus IB. Guys, I hope you guys are following this.
Yes, sir.
So what is free current then? Free current I can calculate using the equation IT minus IB. So here comes what is IT? IT is this equation. What is IB? IB is this equation. So I can write it as contour integral B by mu naught minus M dl. So what is free current? I is equal to integral B minus, sorry, B by mu naught minus M dl. Call this as equation 1. Okay. Now comparing this equation 1, compare this equation 1 with Ampere circuital law, that is I is equal to contour integral H dl. If you compare these two equations, okay, if you compare the components of integral coefficients of these two equations, I can write H is equal to B over mu naught minus M. So here what I did, I compared equation 1 with Ampere circuital law. So I got H is equal to B by mu naught minus M. So what is B is equal to then? So B equal to What is B equal to, guys?
H plus M into mu naught.
Okay. So B is equal to mu naught H plus mu naught H plus mu naught M.
Yes, sir.
Okay. So if I take mu naught constant, so it will be H plus M. So B is equal to mu naught H plus M. Okay. So what happens if it is in free space? So if it is free space, magnetization is what? Magnetization is 0. So magnetization is 0 in free space. M is 0 in free space. So what happens to this equation? B is equal to mu naught H. So this is one more equation which has been derived to say that magnetic field is equal to mu naught H in free space. So this is one more relationship. Remember this relationship. P is equal to mu naught H plus M. So if I want to extend this, what is magnetization? What is the equation for magnetization in terms of susceptibility? So is M magnetization is equal to susceptibility of any given material. I call it as psi M into, what is the equation? Is it H? What is susceptibility equation? Susceptibility was equal to magnetization over magnetic field. So what is magnetization then? Magnetization is equal to psi M. This is psi is nothing but magnetic susceptibility, magnetization susceptibility, psi M H. So if I substitute this equation here, so we call this as equation 2, substitute it to equation 2, I get B is equal to, what is the equation? B is equal to mu naught H plus psi into H. Okay, this is psi M. So now if I take H outside this, so it will be mu naught. What is this coefficient then? 1 plus psi, and this is H. Is this okay? Is this equation okay? P is equal to mu naught 1 plus psi M into H. Call this as equation 3. How does this equation looks like? How does it look? Does it look like mu naught mu R into H? As I am asking you a question, does it look like B is equal to mu naught mu R? So can I equate this 1 plus psi M to mu R?
Yes, sir.
So now, what is mu R? What is mu R? Mu R is relative permeability. This is relative permeability. Mu R is equal to 1 plus psi M. which can be also written as mu by mu naught. This is again another relationship between the permeability of any given material with respect to the susceptibility with mu and mu naught. So what is mu is equal to? Mu is equal to mu naught and mu r. So what is mu r is equal to? Mu r is equal to mu over mu naught. Okay. So 1 plus zeta, sorry, 1 plus psi n. Make a note of this equation also. Okay. Have you noted this down?
Yes, sir.
Okay, fine. So now very recently I obtained an equation here somewhere. Still going here. Okay, fine, here. This is IE is equal to minus IT. Okay, hope you remember this equation, equation 1. I just need to draw some curl concepts here. So let us just try to conclude this set of equations. I can write IB, that is bound current IB is equal to surface integral JB into DS. JB into DS. Okay. This is in terms of M. That is in terms of magnetization. This is in terms of magnetization. And IT. What is IT? Total current is equal to, again, surface integral JT. That is total current density. This is JB and this is total current density DS. Again, this is in terms of B over mu naught. B over mu naught. And what is I? That is free current. I is equal to surface integral J into ds. This is with respect to the magnetic field. So just refer to your equation 1. You will find these coefficients. So this will be like integral MdL integral B by mu naught dl. This is line integrals or contour line integrals, and this is H dl. I is equal to line integral of H dl. Is this okay, guys?
Yes, sir.
And these three equations you should refer to equation 1. So you'll get all these equations. Now what is the relationship between the curl here? So how do you convert the line integral to surface integral? How do you convert the line integral to surface integral? Introduce curl, right? As I need some response here. Can I equate this to surface integral of curl of M ds? This is equal to surface integral of curl of B by mu naught ds. Respond. This is equal to surface integral of curl of J ds. Yes or no?
Yes, sir.
Okay. So now equate these terms. What is curl of M is equal to? Curl of M is equal to JB. Can I write curl of M is equal to JB now? Equating the components of surface integral, I get curl of M. That is curl of magnetization is equal to what? Bound current density. That is JB. Can I write curl of B by mu naught is equal to what? Total current density JT. Can I write curl of, this is curl of H, sorry, this is HDL, this is H. This was H, right? So can I write curl of H is equal to what? J. I am equating the surface integrals curl of B by mu naught is equal to JT. Curl of H is equal to J. So again, these are very important concepts with respect to the magnetic materials. So here we have introduced few terms. This is magnetization with respect to a bound current. This is B by mu naught with respect to total current, and this is curl of H with respect to free current or electronic current. So any doubt?
No, sir.
Okay. So take down a simple problem. So just let me clear this canvas. Okay. So there will be very simple and straight forwarded problems with respect to this content or concept. Okay. So for any given material, so the problem is something like this. Find permeability, take down, find permeability of material. So maybe for next coming video online sessions, I'll be uh, keeping it ready, the questions, the ready-made questions, so that I can simply copy it and paste it so that I can reduce some time. So permeability of material. So you are supposed to find permeability is mu of material whose magnetic susceptibility, that is psi, is given. It is 49. So you need to find mu, knowing susceptibility. What is the equation for mu? Is mu equal to mu naught into mu r? Yes, fast. Is mu equal to mu naught into mu r?
Yes, sir.
Yes.
Okay. So given psi is given, susceptibility is given. So what is permittivity and susceptibility relation?
1 plus psi.
Mu r is equal to 1 plus psi. This is equal to 50. Therefore, what is mu? Mu is equal to 4 pi into 10 power minus 7 into 50, which will be equal to, if you calculate, if you solve this, you'll get 62.8 into 10 power minus 6 ampere per meters. Okay. So take down another problem, second problem. Find magnetic field strength, that is H. You need to find magnetic field strength within a material, within a magnetic material, where first sub question magnetization is given, that is M equal to 300 ampere per meter and mu equal to 1.5 into 10 power minus 5. Oh, Henry per meter. Sorry guys, this is Henry. H by M. See, this mu is represented, of the units is Henry per meters. Mu equals Henry per meter. So you need to find H. The value of H, if the magnetization is known and the permeability is known. Second sub question, if B is given, B is equal to 150 micro Tesla. 150 micro Tesla. Okay, they will get confused with mu. So let me just so this I write it as micro. And theta m or psi m is equal to 1.5 into 10 power, sorry, I'm just writing the same here. So time is equal to, it's an integer value actually. It's 15. What is the solution? What are the equations to find H? Guys, if H is given, if M is given, and if you need to find H, what is the relationship between H and M? H and M are related with an equation psi m, right? What is psi m is equal to? Psi m is equal to M divided by H. Correct? So what is H is equal to? So therefore H is equal to, sorry, it should be a scalar quantity. H is equal to M by psi m. But what is mu equal to? Mu equal to mu naught into mu r. So therefore, what is mu r is equal to, because I don't know this psi m, right? So what is mu r is equal to? Mu r is equal to mu by mu naught. Okay, mu by mu naught. So what is the value for mu by mu naught? So mu is given 1.5 into 10 power minus 5 divided by 4 pi into 10 power minus 7. 4 pi into 10 power minus 7. And you'll get a value as 11.94. Okay, so once you know mu r, what is h is equal to now? So this implies m is equal to h theta m, which is equal to h. What is theta m is equal to, or psi m is equal to mu r minus 1 r. Therefore, h is equal to m over mu r minus 1. And directly substitute it here. So what is psi m is equal to? Psi m is equal to mu r minus 1. And you'll get the value as 300. That is, magnetization is 300 over mu r is 11.94 minus 1. It is 10.94. Which is equal to 27.42 ampere per meter. So this psi m equation we knew. What was psi m earlier? It was 1 plus psi m equals to mu r. Okay, this we have already derived, which is equal to mu by mu naught. You have to remember this equation. Susceptibility is equal to permeability minus 1, mu r minus 1, and you get 27.42 ampere per meter. This is H. So how are you going to find the second solution for second sub question? So B is given, psi is given. Okay, B is given and psi is given. So what is H is equal to? You need to find H, right? So if B is given and psi is given, you need to find H. So B is 150 microtesla and psi m is equal to 15. So what is H? So H is equal to B by mu, which is equal to B by mu naught mu r, which is equal to B by mu naught. What is mu r? 1 plus psi m, which is equal to 7 0.46. Calculate the values for B, that is 150 into 10 power, sorry, 180. Is it 180 or 150? Okay, 150. Yeah. 150 into 10 power minus 6. And mu naught is 4 pi 10 power minus 7. Zeta m is given, that is 50. So calculate, substitute all the values into the calculation. You should get 7.46 ampere per meters. Okay.
Yes, sir.
So there are few things what you need to remember. The relationship between